Okay, so now we move into average rate of change of a function. So now we're starting with calculus language, average rate of change. And the first thing that you're going to discover is that the average rate of change is only the slope. So we're going to look at average rate of change, and we're going to look at linear functions that have a constant rate of change. Functions are used to model changing quantities, and in this section we're going to learn how to find the rate at which a value of a function change as the input variable changes. Now this is simply like when you have y equals mx plus b before in Algebra 1, the m is your slope, and how that changes every time that you put a different value of x in, the slope either rises or it falls. And this is the same kind of concept. So we're all familiar with the concept of speed. So if you drive a distance of 120 miles in 2 hours, then your average speed is 120 miles divided by that 2, which is 60 miles an hour. So now you suppose you take a car trip and you record the distance that you traveled every few minutes. The distance that you've traveled is a function of the time. So S of t is the total distance traveled at time. We graph the function, so notice that as we start, it's not constant. And if you think about it, when you're driving, you don't drive the exact same miles per hour speed limit everywhere you go. So that's why this is going to change shape. So here we have the average speed over 3 hours, and then here is our height, and this is our miles. So we have our miles and we have our hours. So the graphs show that you traveled a total of 50 miles over 1 hour, 75 miles after 2, 140 miles after 3, and so on. So you find your average speed between any of those points. You're going to divide the distance you traveled by the time elapsed. So if you calculate the average speed from 1 p.m. to 4 p.m., the time that elapsed was 3 hours. To find the distance that you traveled, you take the distance, 200 miles, minus the 50 miles where you started, and you'll get 150 miles. So your average speed then would be your distance traveled, that 150 miles that you traveled in that 3 hours, over the time elapsed, which again is the 3 hours. So if I divide the two, I will get 50 miles per hour on average. The average speed that we just calculated can be expressed by using function notation. So S at 4 hours, the distance at 4 hours minus the distance at 1 hour over the time at the end minus the time when you started. So we have, again, you should recognize this right here as, wait a minute, this looks very familiar to Algebra 1. Isn't this the same thing as saying y sub 2 minus y sub 1 over x sub 2? Sorry about my crazy lines again. Over x sub 2 minus my x sub 1 slope. Same concept. I can write it as y sub 2 minus y sub 1, or I can put it in function notation, which is s sub 4 minus s sub 1. So the average speed is different over different amount of time. So for instance, from 2 to 3 p.m., we see that from just 2 to 3, which is 1 hour difference, I traveled about 65 miles an hour. So it depends on the interval that I'm looking at, what my average speed is going to be. Obviously, if I spent most of this time on the interstate, my speed's going to be faster, and maybe some of the time I was off the interstate and going through stoplights and maybe through rural communities, so I have to drive a little slower. So this comes to the average rate of change. So the average rate of change would be, again, slope formula right here, everybody. This is the same thing as y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So you learned this back in Algebra 1 when you learned about slope. Same way you find the average rate of change. So the average rate of change is the slope of a secant line. So here you have your secant line between x and a, and on the graph of f. So that is the line that passes through this first point and this last point. So here's this first point. This is A. So this right here is f of A. See, that's why they have it over here in this corner. This point right here is my A, comma, f of A. Just a coordinate point. Same as saying x, y. Okay, so this is my first point here. And this is my second point here. Now, a secant line is a line that intersects the curve at two places. That's just what this is right here. And then this point up here will be my B, f of B. Two points, slope formula, average rate of change. All the same, nothing new. The only new part is you're looking at a curve and you're taking those 2 points and you're calling it an average rate of change instead of just keeping it all on the same line. So recognizing this function right here, you have something to the second power. So this parent function would look like a parabola. Notice the minus 3. All that did was take that parabola point and move it over to 3. And we're going to study those transformations more in the next section. Anyway, if we have a graph here and we're looking at x equals 1 and x equals 3 and maybe x equals 4 and x equals 7. So we're going to look at the rate here, the average rate of change here, and we're going to look at the average rate of change here. So you can see we're going to get two very different results. I'll take my value at 3, subtract my value at 1. When I do that and I plug in the points, I get 0 minus 4 over 2, and notice I get a negative value, and that's because those first 2 points, as I read it from left to right, I'm going down. So since I'm going down, my slope will be negative. The second 2 points from left to right, I'm going to be going up. So I would guess that when I do this, I will get a positive value, and I do. Now, linear functions have a constant rate of change. This is your y equals mx plus b. Here we have y equals 3x minus 5, or we call it f of x equals 3x minus 5, and we want to find the average rate of change. Well, if it's a linear function, the average rate of change is going to stay the same because there's no curve, because it's linear. So this is your y sub 2 minus y sub 1 over x sub 2 minus x sub 1. and we get 3 at this point. Let's look at this point. And we get 3 at the next point. What do you think is going to happen at this point? Okay, so, and they didn't give you the last point, but the constant would be 3. So here they're saying, now let's look at this line everywhere. So let's look at it at a plus h, and let's look at it at a. Now, a plus h means any distance away from where you started. See that? I'm just going to add a distance from where you started it. If f of a is my starting point, a plus h is going to be a distance away from where it started. Now they're giving you some calculus language here that's going to help you define some things for calculus. That's why they're looking at this. But again, I want you to consider that this means I start at A, and then I just add a distance onto that. Let's see what happens when I plug this into that same equation that I had before. So remember, that equation, which they should have reminded you, and I'll just put it as a y equals 3x minus 5. That was the equation that we started with. And we already know that that slope, we found at those different points were 3 because it's a linear, it's a line. So the slope's the same everywhere. So let's see. If I plug in a plus h into, instead of f of x, I have f of a plus h. And I plug in f of a. Let's see what happens. I'm going to simplify by distributing. Then I'm going to combine like terms. And I get 3h over h. So the h's will reduce. And I see that I still get my slope of 3. So the whole point of this is to show you that no matter where, no matter what distance you move on a line, because it's linear, the slope is going to be the same. For this equation, it will be 3. So again, same thing we just said, no matter where you start, no matter what distance you go from it, if it's a line, the slope is the same.